Welcome to my presentation. My name is Wang, coming from Grant, Austria. It's my pleasure to introduce our recent work, Subspace-Configurable networks. Today, I will give you four parts about our work. Firstly, it's about the introduction to the problem we want to target and motivation. Secondly, I will introduce our proposed subspace-configurable networks, SCNs. Thirdly, I will show you two interesting results for the evaluation of SCNs on IoT devices. Finally, you will get some takeaway from my side. So I would like to target the problem in model adaptation, especially when you consider the data in deployment. So the general process of model training or fine-tuning or applying transfer learning can be described as follows. You start training your model or fine-tune your model or transfer learning data site. And then you are going to do optimization to just enhance the generalization abilities of the parameters. And before deploy your model to the device for your target environment, it's necessary to compress model's parameters to accommodate limited storage space in real-world environment. Then you deploy your model in the target device and environment. Congratulations, that's perfect, but is that enough? No. What about if your camera is not mounted as you expect during training? You may have a mismatch between training environment and deploy environment. In many cases, your input data is transformed. The input transformation is widely extended in many data domains. For example, in computer vision, we may have rotation, scaling, translation, brightness changes, contrast adjustment, which are important to the computer vision-based technologies like self-driving car by Tesla, which the model do the work or perform reliably. In audio domain, we have some transformations like volume control, frequency adjustment, and noisy filtering. Similarly, in time theory data, we have cropping, shifting, resampling, and so on. So we wish a model in real world could work robustly. For example, the model should generate the same result of rotated image of a dog. The question is how to implement this one, how to make model robustly and efficient to data transformation. Someone may say, let's do data adaptation. You can firstly do data augmentation. Just provide all possible transformation to the model, and you wish the model could learn this transformation. But unfortunately, this is not guaranteed, and you may need a larger one. Or you can do on-device adaptation, but you need labeled data, which is quite expensive. Or you can design a very advanced invariant architecture, go back to 30 years ago, you were the Yang proposed the convolutional layer plus max pooling, but it's not straightforward. For specific transformation, you cannot always find the architecture by yourself. And you can also track localization of data. You just convert the data into a very simplified format to simplify task. Unfortunately, this is also expensive to require more data, and you may also need a larger model to handle ability. So here we introduce subspace-configurable networks, which makes inference implicitly. Subspace-configurable networks. 3 words means 3 parts of the architecture we proposed. In the right side, you can find the whole pipeline or whole project of our proposed method. No worries. I will split the whole pipeline into 3 parts. Firstly, let's say you have a continuous transformation T. It could be rotation, translation, latency, intensity, like 200 looks, 20 meter, 20 pixels, 30 degree, 100 degrees. They are the transformation parameters we call the R. So you are going to feed the transformation parameter R into a configuration network, which is a hypernetwork implemented by 1 layer, fully connected layer, just a simple MLP layer. And this configuration network will generate a low-dimensional space, like a vector beta 1, beta 2, beta b. The dimension of this low-dimensional space can be determined by your task or by your requirements. Let's say we have for d equals to 3, which means this dimension of this beta is 3, like 0.1, 0.2, 0.6. And then we're going to train D-based models of the same architecture in the same computational graph. And they have the same architecture, but we trim them together, and then we construct the final inference model just by ensembling or weighted summary the weights of these D-based models together with the configuration vector beta. You have the final inference model theta. And then you feed your transformed input, like rotated the image of a dog into your inference model theta. You get the final prediction y. But the question is, why could this method work? Okay, because it always chooses the best combination of the weights of high accuracy model from the subspace. Then the final inference model can be used for such transformation parameters. Okay, here is the final pipeline for the subspace-configurable networkers. I would like to ask you a question. Does this architecture remind you of something, especially in large language model? And I will give you 5 seconds to think about this question. Yes, exactly. It's MOE, mixture of experts. You can think about the SCN model as kind of a router to effectively generate low-dimensional coefficients and then configure the inference model with from the base model. So it's more efficient. Then let me introduce the performance of our SCN model. Okay, we evaluated our SCN model on different combination of model modality, data modalities, and model architectures. For example, 3D point cloud data with 3D rotation projection, 2D images with rotation, scaling, translation, brightness changes, contrast adjustment. Also in audio data with pitch shift, speed changes, and so on. I would like to highlight one result of ResNet 18 trained on C14 dataset with rotation. And from the right plot, you can find some baselines. The first one is the one-for-all model. One-for-all model means the data augmentation method. In the between, you can find the 5 values of SCNs with different dimensions from d equals to 1 to 2, 3, 5, and until to 8. If you increase the number of dimensions of D, you can find the performance of SCN ResNet 18 on the C14 data set with rotation. They can always get better results and can almost achieve the same performance as the remaining two. The remaining two are the comparison baselines for inverse transformation method and 1-for-1. So inverse means the inverse transformation applied by just do the inverse transformation, but only available for one single transformation parameter. It's also a kind of theoretical upper bound of the method, because we just train the model on the original site without any data augmentation. And if you see the trade of the SCN model in between, for example, for 3, 5, 8 different dimensions, they looks very similar, can all achieve the similar performance. It's good because you do not need a high dimension. You just need a 3 base model or 5 base model. You can achieve similar result, which is good to the resource limited devices. I would like to show you a beautiful visualization with the configuration space, the subspace, beta, and the transformation parameter alpha. Okay, if you look at the left plot, if you change rotation degree from 0 to 360, I think I can always choose the best combination of betas. You see, it's different degree, and accordingly in the right plot, you see the texture entity of SCN on the specific rotation transformation parameters. Looks very good. It can achieve almost the same performance and the inverse, and it's much better than the one for all method. Similarly, in a more complex transformation, 3D rotation plus projection, you first rotate a 3D object and then project it into a 2D plane. For example, this is an example object from model net 10 dataset consisting of 10 classes of 3D point clouds. And we just utilize Learnet 5 model, which is very old school, but very efficient to solve the problem. We have some baseline from DX to 1, 2, 3, and 5. Okay, if you have a look at the DX to 1, so I think always choose the only value from this data, only base model. If you increase D to 2, you have 2 base models. You can get the cosine of sine like beautiful surface. And if you increase D to 3, you have 3 base models. You have some like cosine of sine like a periodical wavelet. But I think always choose different beta from different dimension of the subspace. If you choose DX to 5, you have more cosine sine like surface, but it's also kind of combination of different knowledge from these 5 base models. Looks very beautiful. And someone may say, if you have no idea about the transformation parameter alpha, that's no problem, because we provide 2 solutions. First one is alpha search. We're going to estimate the most probably alpha based on the model's confidence. Secondly, you can do the sensor inference, just take the sensor value from your MOU if you deploy your model to a resource-limited device, like an IoT environment. Okay, in terms of IoT devices, I would like to show you 2 interesting results of evaluating the thinking models on IoT devices. First task, fruit classification, which is widely used in smart agriculture. We want to filter out the different or disqualified fruits. However, lightness intensity may affect accuracy. With a higher lightness intensity, a bad apple may be recognized a good one. That's not good. So in this demo, IoT experiments, we collect some RGB data and lightness intensity from bananas, apples, oranges, lemons, kiwis. We want to deploy our model to Arduino Nano 33 Bluetooth synth with only 256 kilobits as RAM. And this is very tiny device. So we just take the RGB value as the input to the model to do the classification, and take the lightness intensity and the input to the configuration network. Let's see some result. On the evaluation of I think on such devices, there are 3 resource consuming parts: Hypernet working spheres, which is for the configuration network, and the configuration, which is just used to do the configuration to do the weighted instant volume. The final inference, okay, we have some baselines, SCN MLP, D equals 3 and D equals 5. And we have model fit in data augmentation method, and one for our range means wider and deep MLP model. Okay. If you go to the left part, you see a 4 plots from top to bottom. It shows the running time, test accuracy, memory usage, and consumption. In our SCN models, D3 and D5, the inference parts only consume almost the same as the one-form model. And the most resource consuming part is configuration, but still 0.3 or 5, even 1 millisecond. But if you increase the number of layers or increase the number of channels in your model, you need more running time, but you cannot get or guarantee the performance improvement if you can look at the test accuracy. You see, the SCN model can provide much better performance in test accuracy, but depending whether one-form model cannot achieve high accuracy with the rotation, with the transformation. Sorry, in terms of memory usage, because we need D-based models, and we can utilize the low-speed space, for example, the Flash, who can store all D-based models in the Flash and just run the final inference with run. That's perfect. And in terms of any consumption, you can find similar trends as well. SCN model consuming a little bit, 0.08, something like that. But if you need more layers or channels, your model needs more energy, almost 9 times larger energy budget. That's not good. But for SCN, it can efficiently provide robust results and use a little bit energy and running time. And the second task is to German traffic sign benchmark. It's very important for the smart traffic or the self-driving car to recognize traffic sign correctly and reliably. The problem is that the rotation of the traffic sign may affect the result. In order to make a robust model in the smart traffic, we are going to implement SCN on the German traffic sign data classification task. The dataset consisting of 43 signs captured on German roads, and we take the rotation degree or the rotation angle from MU and put the captured image and the input to the final inference model. We deploy the model to ESP32S3i development board with 8 megabit PS RAM and 8 megabit flash, which is larger enough to the compute automation task. Similarly, we have SCN LearnNet 5, DX3, and DX5. And we have baselines, one for all LearnNet 5, which is data augmentation, and one for all range, deeper and wider LearnNet. And here, in the left plot, you can also find the result between SCN models and other deeper and wider one-for-all model. But the gap between SCN and others is huge, much huge, you see. Similarly, SCN only needs a little bit running time, but the wider and deeper model need more running time, but they cannot provide better test accuracy. Even the one-for-all 4 times wider model can only achieve the performance of SCN-DX3, but they need more running time, more memory for the model, and more energy consumption. Okay. And if you look at the SCN model on this SCN LearnNet 5, you find that the inference is the most energy consuming and time consuming part, but the hypernet inference and the configuration consume almost nothing there, 0.2 compared to 47. So SCN would be a better choice compared to other deeper and wider models. Okay, finally, I will provide some takeaway. SCN models can learn the configuration subspace and generate optimal model for your given transformation parameters. It's very resource efficient method to model adaptation. And you can also apply in other data modalities. For example, in our paper, we also evaluated the SCN audio data and other transformations. And you do not need a very large base model. You just need a small one like MLP or learned 5 as enough, but it can still provide good result. And you also do not need a high dimension. You just need them equals 2, 3, or 5, something like that. And the most any constant pushing of SCN always happens in the final inference. We just use the base models to do the ensembling on summary. So it's a faster inference. And you can also place SCN partially on your model. For example, we can do block-wise SCN or ResNet 18. So in our paper, appendix, you can find Wang experiments showing that if you just apply SCN on one block or some blocks of the ResNet 18, the ResNet 18 can still has the ability to do well in the CFR10 data set with 2D rotation. Currently, we are working in SCN on YOLO V5. We think the SCN can help the rotation situation in object detection problem. And in the future, we are going to study generation ability of SCN on the out of distribution data. And we also want to do parameter efficient model update method. Thank you for listening. And if you want to know more about our work, please scan this QR code. You can find the released code, visualization webpage, and podcast discussion generated by AI, and the IoT parameters data. You can also have a look at our group's work by this final link. Thank you so much.